Edexcel Core Pure, Calculus 3, Inverse Trigonometric Functions, Differentiating arctan x. There are two main ways of representing the inverse tangent function. There is the more formal arctan x notation, but there is also the tan minus 1x notation, particularly used on a calculator. And it's very important that we do not confuse, but if we're going to use this notation, that tan minus 1x, the inverse function, is not the same as a reciprocal. So we mustn't confuse 1 over tan x with tan minus 1x. They are not the same thing. Just for consistency, we're going to be using the notation arctan x during these presentations. So looking at the graph of arctan x, we can see that the domain of this function x can go for any real value. X can be any value from minus infinity to plus infinity, but that the range of the function goes from minus pi by 2 to plus pi by 2. So that's the definition of the range. It's also a one-to-one mapping in order for this inverse to be defined. And if we start to look at the gradient of this arctan graph, we can see no matter where you draw the tangent to this curve, the gradient will be at least 0. It never has a negative gradient. So the gradient is going to be at least 0, and that's a point that we're going to need to use later on in the presentation. So now if we look at differentiating arctan x, the neat way of differentiating this is to rewrite it as x equals tan y. So we go back to the trig function tan y. And now if I differentiate both sides with respect to x, we will need to do this implicitly. So if I differentiate x with respect to x, we'll get 1. If you differentiate tan y with respect to x, you're going to get sec squared y. And then because it's implicit, dy by dx. Now I'm going to rearrange for dy by dx, and when you do rearrange, don't lose the sec squared y. So you want to leave it as 1 over sec squared y. Don't write it as cos squared y. And the reason being, we want to now use the fact that sec squared y minus tan squared y is 1. We're going to use this identity as a way of rewriting sec squared y. So dy by dx will become 1 over, and sec squared y is 1 plus tan squared y. And at this point we need to remember that tan y can be written as x. So dy by dx is 1 over 1 plus x squared. So that is the standard way of differentiating y equals arctan x. So just to recap a couple of those key features, if you want to differentiate arctan x, you can rewrite it as x equals tan y. Then we differentiated it implicitly with respect to x, and then we rewrote sec squared y as 1 plus tan squared y. Then we used the fact that tan y can be written as x, so it became 1 over 1 plus x squared to get this derivative of arctan x. So if we now go back to the graph of arctan x and we look at the gradient and features in a little bit more detail now, so we know that the gradient function is 1 over 1 plus x squared. If we look at x equals 0, so if we look at the origin, when x equals 0, the gradient function will be 1. So the gradient of this curve is 1 at the origin. However, we can see as we go along the curve that it, for example there, that the gradient is shallower than 1, and if we go to another point, it is also has a shallower gradient than 1. So at the origin, the gradient is 1, but everywhere else along the curve the gradient will be less than 1, so it will be less steep than y equals x, which means that the gradient is bigger than 0 but less than or equal to 1 along the curve y equals arctan x. So now we're going to look at the more general derivative of y equals arctan x over a, where a is a constant. And again, we're going to rewrite this as x over a equals the tan of y. So we go back to the trig function tangent, and we're going to differentiate with respect to x, both sides. So differentiate x over a with respect to x is 1 over a, and differentiate tan y with respect to x, it will become sec squared y, and the derivative needs a dy by dx because of the implicit nature of this differentiation. So dy by dx equals 1 over a sec squared y, just rearranging. Don't rewrite this as cos squared, leave it as sec squared y. And then we're going to use the fact that sec squared y is 1 plus tan squared y, and we can use this identity to replace sec squared, so it becomes dy by dx is 1 over a sec squared is 1 plus tan squared y, and then we can use the fact that tan y was defined as x over a and reintroduce that, so this becomes 1 over a 1 plus, and tan squared y will be x squared over a squared, and if we lose the bracket now, expand the bracket, we get a plus x squared over a, and the standard way of writing this answer is to times top and bottom by a. So if I times the top by a, we get 1 times a, and if I times the bottom by a, we get a squared plus x squared as the denominator. And that is the more general derivative of arctan x over a. So the key things to remember: rewriting the inverse function as tan y is x over a, differentiate it implicitly with respect to x, and then we've used the identity sec squared y is 1 plus tan squared y, and then when we have tried to simplify this problem, we have replaced tan y has been replaced with x over a, and then we've put this over a common denominator in this case of x squared before we've expanded the bracket. And if we times the top by a and the denominator by a, we end up with a over a squared plus x squared. So we have this useful standard derivative, if you like. If you differentiate arctan x, it's 1 over 1 plus x squared, but the more general case is the one that will give you more options. If we look at the more general case, that the derivative of arctan x over a is a over a squared plus x squared. Notice the a up there, that will be useful and important later on. But if we replace a with 1, the special case that a is 1, we go back to the standard derivative as seen. We're going to be using these results later when we start to introduce integration into our methods. In the next session, we're going to look at integrating using arc sine x.